Swayam Prabha. Digital India. Educated India.
Dear all, we will continue the next idea is cyclic group. Already we come across the full detailed about group, the same group you take it and which is cyclic. If there is an element A in G such that every element of G is some powers of A. See, for example, you take G is equal to 1 minus 1 I comma minus I. Now you have I power 1. First of all, G is a group. So, quadratic 4 group. This is quadratic 4 group. It means it satisfies the group property, and you start from I power 1 is I square equal to minus 1, I cube equal to I square into I, which is equal to minus I, and I power 4 equal to I square into I square, which is equal to plus 1. C, it means the power. So, it has a 4 element, and that element of start from 1 power 1, 1 power 2, 1 power 3, 1 power 4, because number of element is 4 element you have to check it out, all are 1. You take minus 1, minus 1 whole power 1 is minus 1, minus 1 whole power 2 is plus 1, minus 1 whole cube is minus 1, minus 1 whole power 4 is plus 1. So, the values 1 and minus 1 only will come, whereas if you take I and see all the elements in the set also reflected, I reflected, minus 1 reflected, minus I reflected, 1 is reflected. Therefore, it is called it as generator. So, a set having the generator and then the set is said to be cyclic, and then number of element is here 4, and that I power 4 should be 1 will come, and rest of the elements should be rest of the powers should be rest of the elements should come, and if it comes all the entries in the powers of this one, then it is said to be cyclic. Now, you go for I power 5, I power 4 into I power 4 into I will come. Now, you see that I power 4 is plus 1 into I is I. So, once again cyclically it comes. So, it is called it as cyclic. So, this way we can understand the beauty of cycle, and then we have some powers of A. So, powers of A here, powers of 1, 2, 3, 4 and so on. So, G is a group is said to be generated by A, and A is called the generator of G. For example, G is an infinite cyclic group, then the generator is 1 comma minus 1, like that we can form a cyclic group. Further example, some example of cyclic groups. You take set of all integer and operation is plus is a cyclic group with 1 is a generator, because 1 you take any number add with 1, and then after ending number with 1 cyclically it comes, and a very good example is integer modulo n is a cyclic group. For example, integer modulo 2 you take it, it comes class 0, class 1 and C in a Cayley table, right. We can easily understand that what cyclic. So, 0 plus 0 is 0, 0, 1 and 1, 1 plus 1 is 2, under modulo 2 is 0. Therefore, it is what a group, and then you go to the what next number 1 plus 1 is 2, 2 under modulo 2 0, and then add 0 plus 3. So, 3 comes under modulo 2 is 1 will come. So, cyclically the value will come 0 and 1, therefore, it is a cyclic group. keep it in mind this, we have a theorem, every cyclic group is abelian. So, cyclic group now you understood, abelian also you know that A dot B equal to B dot A, then it is said to be commutative or abelian. So, you take any cyclic group elements or in a group and then check it out whether they are abelian or not. So, let G comma star be a cyclic group with the generator A. So, you take an element x comma y in G. So, x equal to a power n and y equal to a power m. Then we have a commutative property A star of B, that is x and y you multiply, so that it becomes a power n star a power m, which is equal to a power n plus m, which is equal to a power m plus n, which is equal to a power m into a power n by law of indices. Therefore, this represent y, this represent x. Therefore, we take LHS x star y we taken and we got the RHS is y star x will come. So, it obeys the abelian property, and we taken that the elements from cyclic group and it obeys abelian. Therefore, all cyclic group is obeys the abelian property, implies every cyclic group is abelian. Now, we have an example, the set of integer z under ordinary addition is cyclic. You take 1 and minus 1 or the generator, and we have a addition 1 power n is interpreted as n once times, and if n is negative then minus 1 times we have what corresponding positive integers we can do for generator. Another example, integer modulo n, you take it 0 to n minus 1 for n greater than or equal to 1 is a cyclic group under addition modulo n. Here 1 and minus 1 are the generator, and we have n minus 1 are generators. That is another examples of integer modulo n. Another example, U10 is equal to 1, 3, 7, 9. This can be written as the generators 3 power 0 is 1, 3 power 1 is 3, 3 cube 7, 3 square 9. Now, 3 is a generator. Also 1, 3, 7, 9 can be written as 7 power 0 1, 7 cube can be written as what 7 square into 7. So, already 7 comes, 7 square comes 14, 7 cube also 21 into 7 comes. So, both obeys the what generator of U of 10. So, this way we can write the generator of a set, and we have a criteria. If the two generator AI and AJ, if AI and AJ are equal, if and only if I equal to j. And example, you take 1 minus 1 I minus I. So, I power 4 I is a generator and minus I is also generator. Therefore, I equal to j. Here it has a finite order, the number of element is finite, and then the Killian group of E square a power n minus 1, where AI equal to AJ if and only if n divides I minus j. So, for the corollary, if you take modulus of A equal to modulus of generator for any group element, modulus of A equal to modulus of A of generator. So, if A power k equal to E implies that modulus of A divides k, or modulus of A or cardinality of A. The cardinality of A means the number of generator in that set. So, in any group element A mod A, cardinality of A is equal to cardinality of generator. If the already we discussed 1 minus 1 I minus I, like it is very simple example, so that understand. Here I power 4 equal to 1, which is equal to E, here identity element, therefore A power k. So, here k element A power k equal to E implies definitely what? Cardinality of A divides k. So, let G be a group and let A be an element of order G, then A power k equal to E, then n divides k. So, this way we can understand the cyclically we can find out the value of A and A under modulo of this. So, A equal to A power 7 and A power minus 5 are equal. A power minus 6 and A power 6 is identically equal to A power 0, like that. Corresponding generator of each element we can write A power 0, A power minus 1, A power minus 2, A power minus 3 and so on. We can easily calculate it, and it comes cyclically how to generate the numbers. And also we have a theorem, we have a generator. The generator can be written as number of element comma generator of the greatest common divisor works definitely. N is a number of element, k is generator. So, definitely the GCD is works 4 and A power k is works. So, if I have a G equal to 1 minus 1 I minus I and N equal to 4 and k equal to 4, therefore, the GCD of k 4 comma 4 greatest common divisor of this one, you take it 4 and then A power k equal to A power 4, here 4, so it works. So, this way we can write the generator of a number. Next corollary order of elements is finite cyclic groups. For finite cyclic group we take it, so the order of elements divides the order of the group. You take G is equal to 1 minus 1 I minus I is what is a cyclic, the number is, the cardinality of G is 4 and then the order of G is also 4, the 4 divided by 4 exactly exists. And also you have a subset 1 minus 1, this is also having the generator, this is order of H is equal to 2, here order of G equal to 4, therefore order of G divided by order of H, this is called as a Lagrange's theorem of cyclic group. Next corollary, we have a criteria that generator AI and AJ. Therefore, cardinality of AI and cardinality of AJ are equal, just we saw that. I 1 minus 1 I minus I is a generator, minus I is a generator, same having the same order. So, they works, therefore, cardinality of A equal to n, therefore, generator of AI and AJ are equal if and only if the GCD of Ni and Nj are equal, implies the cardinality of AI equal to AJ if and only if the GCD of n comma I equal to GCD of n comma j. So, the generator of a finite cyclic groups, if cardinality of A equal to n and A having the generator AI, AJ, if and only if the GCD of n comma j equal to 1 and cardinality of A is generator AJ if and only if the GCD of n comma j equal to 1. And we have a generator of integer modulo n and integer k in Z and the generator of Z1 if and only if GCD of n comma k equal to 1. Next, fundamental theorem of cyclic groups. Every subgroup of cyclic group is cyclic. This is a very important statement. Moreover, if cardinality of A generator is n, then order of any subgroup of A is a divisor of n. It is an interesting one. And for each positive divisors of k of n, the group A has exactly one subgroup of order k, namely a power n divides k. So, moreover, we have if k is a divisor of 30, the subgroup of k is a power 30 by k. So, that the list of generator A is E to 29 the order is 30, E to 28 the order is 15, because 30 by 2 that is 15. So, we can have number 2 is power, simply divide it, and then you have a cube as E a cube and so on a 27, and 30 by 3 is order is 10, and then 5 a power 5 having the generator like this, and then 30 by 5 it becomes order is 6, and here a power 6 is generator, and these are all the possibilities of the subgroup of order, and then 30 by 6 then order is 5. So, like that a power 10 order 3 and order 2, and a power 30 is corresponding generator of the general set, obviously it is E, therefore, it is order 1. So, in general of order 30 as we discussed, so generator has order n, then k divides n, then a power n divides k is a unique subgroup of order k. Next subgroup of integer modulo n. For each positive divisors k of n, the set n divides k is a unique subgroup of Zn order k. Moreover, these are all only subgroup of Zn. So, for example, the list of subgroup of order 30 is 1 equal to 0 to 29, the order is 30. For 2 we have 0 to 0, 2, 4, 28, and then order is 15. For 3 multiple of 3 is 0, 3, 6, 27, and integer modulo 30, integer modulo 30, and then you have to take a multiple of 2, and then multiple of 3, multiple of 5, multiple of 6, multiple of 10, multiple of 15, multiple of 30, then corresponding order using the theorem, then we have a order, and then this order is unique, and these are all the only subgroup of integer modulo n. Also we can list the subgroup of integer modulo 30. So, the number of elements of each order in a cyclic group, if D is a positive divisors of n, the number of elements of order D in a cyclic order n is total function of phi of D. So, if D is a positive divisor of n, note that point. So, if you take n, what are all the positive divisors that you have to find out. So, the number of elements of the order D in a cyclic group satisfy this condition. For example, you take 1, number of divisors of 1 is 1, therefore, phi of 1 is 1. You take 2, the number of divisor is only 2, therefore, phi of 2 is 1, and then 3 you take it, then 1 and 3, therefore, 2 will come. 4 you take it, 2 and 4, therefore, 2. Phi of 5, the positive divisors of 5 related to this one is 4. So, phi of 5 equal to 4. So, like that already we discussed in number theory that Totian function, and it obeys that the number of elements of each order in a cyclic group, and see in the cyclic only it comes. So, number of element of order of D is a finite group. In a finite group, the number of order D is divisible by phi of D. So, let G be a finite group of order M. For G belongs to G, define the set G power 0, G power 1, and so on. This is the order of G, and we can define the finite group corresponding to generator. So, at the end of the power of m we can denote, and n 1 will come, that is a generator, and this value is less than or equal to m is the smallest positive integer, and then g power I equal to 1, the above sequence repeated I terms, then g naught, g1, g power I minus 1, where g contain at most I element. In fact, it contains exactly I element and forms a subgroup of G, is called subgroup generated by G. So, by definition, let G be a finite group, and G in G, then order of G is the smallest positive integer I, such that G power I equal to 1, and equally the order of G is equal to cardinality of the generator. So, if G be a finite group and G belongs to an element of order I, then the two generator G of x equal to G of y if and only if the power of the element x is equal to y under modulo I. So, this is the proposition we can infer from the generator, and if there exists a G in G, the whose order is equal to that of the group, then the generator equal to G. In this case, G is a cyclic group, and we have a generator of G. So, every set having a group property with the generator, then it is said to be cyclic group. And we have a proportion, let G be a finite group of order m. Say G in G has order I, then I divides m, its equivalent, it is, or more or less like Lagrange's comes like that. So, let G be a finite group of prime order P, then G is a cyclic. Further, all elements of G except the identity element generator of G. So, this way we can write the example of additive group under modulo 12 is a cyclic. So, what elements are generator that you have to find out. Is multiplicity group integer modulo cyclic? Check it out. And how about the multiplicity group of integer modulo 7? So, if P is a prime and then integer modulo P is a cyclic group, then it has order P minus 1. So, this way it is what we can bring the idea from number theory to cyclic group. So, from this definition we can infer an example, G be a cyclic group of order n and G in G, and it has a generator, then the mapping of integer modulo n to G given by f of a equal to G power a is an isomorphic between Z and G. Indeed, a and a dash in integer modulo n, we have f of a plus a dash equal to G of a plus a dash under modulo n, and then G of G power a plus a dash equal to G a into G a dash equal to f of a into f of a dash. So, it means isomorphic. Isomorphic mean a map f such that x to y, and then f is homo, and then f is homo mean f of x star of y equal to f of x star of f of y. Therefore, it follows the homomorphism, and f is bijective means it is both one to one and on to. So, this way we can define it is isomorphic. It obeys the isomorphic ideas between Z and G and integer modulo Z to given group G. G is a cyclic group. So, next one is a discrete logarithm. Computationally and in a cyber security, these ideas is very helpful in a Diffie-Hellman and so on. Now, if G is a cyclic group of order Q, then there exists a generator G in G such that G power 0, G power 1 and so on g power q minus 1 equal to g. Put another way, for every h in g there is a unique x in zq such that g power x equal to h. So, we call this as the discrete logarithm of h with respect to g, and we can write x equal to log h base g. So, this way the discrete logarithm ideas may come. That is why I taken the snap, and then even it generate like that, cyclically it will grow. Next, discrete logarithm problem says that if d of log a comma g of n Galois of n of a polynomial n running over, to obtain g q g, then g is a cyclic group of order q, and cardinality of or norm of q equal to n, and g is a generator of g. This is the first step we have to do with the help of the discrete. Choose h from g, and this can be done choosing x dash in integer modulo q, and we have a generator h is equal to g dash, and a is given in g q g h, then the output is x belongs to zq. The output of the experiment is defined to be 1 if g of x equal to h and 0 otherwise. So, we say that the discrete logarithm problem is hard related to g if for all probabilistic polynomial time algorithm, the script A there exists a negligible function negl such that, and a probabilistic of d log ag of n equal to 1, it should be less than or equal to a negligible function of n. So, this way the discrete logarithm problem is defined. Next, computationally Diffie-Hellman problem corresponding to the generator, and fix a cyclic group G, and a generator G in G is given two group H1 and H2, and DHG of H1 H2 is defined as G of log of H1 base G and log of H2 base E G, that is given H1 is equal to one generator, H2 equal to generator, then DH of this generator is G of x into y, which is equal to H1 y equal to H2 x, H2 power x generator. Next, Diffie-Hellman problem is compute with DHG of H1 H2, where randomly we are chosen H1 and H2. So, we have to make a note of discrete logarithm problem is easy related to some script G given the random chosen H1 and H2, so that the Diffie-Hellman that is computational Diffie-Hellman is work. Therefore, the converse is not work and not clear properly. So, the decisional Diffie-Hellman problem says that, so it is distinguished between the DH H1 of H2 from the random group element for randomly chosen H1 H2. So, we say that decisional Diffie-Hellman problem is hard related to script G, because the condition of this one is probabilistic polynomial time algorithm of script A, and there exists a negligible function negl such that the probability of script A of g q g g power x g power y g power z is 1, and which is equal to negative of probabilistic of A of g q g g power x g power y and g x y equal to 1, and which is negligible of the function n. So, this way we can define the decisional Diffie-Hellman problem, wherein the case of probability are taken over the experiment of g power 1 power n is output, we have g q g and randomly chosen the values of x comma y comma z. For discrete log and Diffie-Hellman, group of prime order are preferred the following, and we have some reason why. So, discrete logarithm problems seem to be hardest in the group of prime order, and finding a generator is really easy, and every non-zero component exponent will be invertible under modulo q, and we required some security proof, and Diffie-Hellman discrete Diffie-Hellman boils down the distinguish between the H1 H2 DHG of H1 H2 and H1 H2 Z for random H1 H2 Y. So, a necessary condition for DDH to be hard is that DHG of H1 H2 be indistinguishable from the random group element when Q is a prime. This is nearly true. So, these are all the things you have to remember in the analysis of Diffie-Hellman ideas, that is group of the form integer modulo p where p is a prime. Give one class of cyclic group in which discrete logarithm problem is believed to hard, and if p is greater than 3 and integer modulo p does not have a prime order, and then it was still the decision Diffie-Hellman problem is not hard in such groups. So, it is working in group that an element y in integer modulo p is the rth residue modulo of p if there exists h in integer modulo p such that y equal to hr under modulo p exists. So, according to division algorithm, if let p equal to r q plus the remainder is 1 with p and q are prime, then the G can be written as the generator H of order R under modulo P. So, H in integer modulo P is a subgroup of integer modulo P of order Q. So, the generator is a uniform element of G. Choose the uniform element H in integer modulo P and compute H power R under modulo P. So, we have to test whether an H in integer modulo P, and also G can be done by you choosing H power Q equal to 1 under modulo P. So, that G is a generator under modulo P and H is equal to Gi, therefore, H power Q equal to 1 under modulo P can be written as G power IQ equal to 1 under modulo P, therefore, IQ is equal to 0 under modulo P minus 1, therefore, RQ divides IQ if and only if R divides I. So, H is equal to Gi which is equal to G into C power R equal to G power C whole power R for some C. So, G has a prime order, so every element of G is a generator. So, generating a uniform element of G is a algorithm, a group generation is algorithm is generated, and for security parameter L equal to ln n, for the output cyclic group of G and its prime order Q and generator G is required, and a uniform n bit prime Q required, and uniform L bit prime such that Q divides P minus 1, details omitted. Choose a uniform H in integer modulo P and H is not equal to 1. So, you have to set H is equal to G is equal to H power P minus 1 under modulo P and return PQG, so that you can understand the algorithm. Therefore, G is the order Q of subgroup of integer modulo P. So, this way we can generate in a cryptograph of the group theory and cyclic group. Thank you.